So today we'll be discussing Hausdorff spaces, which are really important types of topological spaces, which appear a lot in smooth manifold theory and manifold theory in general. So first we should define what a Hausdorff space is. So a topological space X with a topology tau is called Hausdorff, which is also abbreviated T2, if for any two distinct points, P1, P2, P1 not being equal to P2, there exist open neighborhoods U1 of P1 and U2 of P2 such that U1 and U2 are disjoint. So in other words, a Hausdorff topological space is one where any two distinct points can be separated from each other by open neighborhoods. So let's give some examples of Hausdorff spaces. The first example is that every metric space is Hausdorff. Now we can prove this as follows. So suppose we have a metric space X with a metric D, and we pick any two arbitrary points P1 and P2, which are distinct and arbitrary, obviously. And we want to show that there exist two open neighborhoods around P1 and around P2 that are disjoint. So let's define the set U1 to be all X such that X is in X, and the distance between X and P1 is less than the distance between P1 and P2 over 2. And we define U2 analogously, but with P2 instead of P1 right here. Now, the first thing to notice is that obviously P1 belongs to U1 because the distance between P1 and P1 is 0, which is less than this. And P2 is in U2 because the distance between P2 and P2 is 0. Now, what we have to prove is that U1 and U2 are disjoint, which is equivalent to proving that if X belongs to U1, then X does not belong to U2. Now, the statement X does not belong to U2. The statement X belongs to U2 implies X does not belong to U1 is logically equivalent to this statement because these two statements are contrapositives, right? So all we need to prove is this one right here, to prove that these two are disjoint. And to do this, we consider the triangle inequality. The triangle inequality which states that the distance between X and P1 plus the distance between X and P2 is greater than the distance between P1 and P2. Right? Now, if X belongs to U1, then this distance, by definition, is less than the distance between P1 and P2 over 2. Now, less than or equal to. In order for the triangle inequality to hold, we need this distance, the distance between X and P2, to be greater than the distance between P1 and P2 over 2. Which means by definition, that x does not belong to U2, because it being in U2 implies that it's less than this distance, which completes the proof that U1 and U2 are disjoint. Now, since our points P1 and P2 were arbitrary, this works for any 2 points, distinct points, in a metric space X, which means that every metric space is Hausdorff. Now, to give an illustration of what we just did, if we have some metric space X, right, and 2 distinct points P1 and P2, what we've done is we have considered the distance between P1 and P2, and we considered, let me make it bigger maybe, the open ball, in blue here, we consider the open ball with the radius, the distance between P1 and P2 over 2, and we did the same for P2. Now these 2 open balls contain P1 and P2 respectively, and they are disjoint, which completes the proof that every metric space is Hausdorff. Now the next example of Hausdorff spaces is a little more easier, and it states that every discrete topological space is Hausdorff. Now, to prove this, consider any 2 distinct points P1 and P2 in X. So space X with topology tau, as always. Consider 2 points that are distinct. Right? Since we are working with a discrete topological space, so discrete, we know that the singleton set P1 belongs to the topology, and the singleton set P2 belongs to the topology. Now, P1 is obviously contained in the singleton set P1, and P2 is obviously contained in the singleton set P2. And since these 2 points are distinct, these 2 sets are disjoint. And since P1 and P2 are arbitrary, every discrete topological space is Hausdorff. Now I wanted to do a more interesting example of proving that something is a Hausdorff space. And here we have this example. Let X be a topological space such that for every P in X, there exists a continuous function f from X to R such that the inverse of 0 is P. And we want to show that X is a Hausdorff space. So first I wanted to review the definition of a continuous. So the definition of continuity in topological spaces. So let me phrase it like this. A function f from a topological space X to a topological space Y is called continuous if for the preimage of every open subset is open. And you might notice that this definition of continuity is basically analogous to the epsilon delta definition of continuity in the Euclidean space, right? Every open subset in Y has an open preimage, right? Now, we can use this to prove this theorem. So let P in X be arbitrary. Be arbitrary. All right. Consider, now by definition, there exists a continuous function such that f inverse of 0 is p. So consider f of x. Right? We know that f of p is equal to 0. Now, for a point, so for every, let's call it x, in x, f of x, and x distinct from p. Since f is a function, f of x is not equal to 0. So fix an arbitrary, let's call it p2 distinct from p, right? F of p2 is equal to some, let's call it r2, which is in R, obviously. So f of p2 is equal to some r2. Since we've proven that every metric space is Hausdorff, and the real numbers are a metric space, we know that the real numbers are Hausdorff. So there exist open neighborhoods let's call them U1. I need more space here. So fix open so there are open neighborhoods. Let's call them U1 of P and U2 of P2, such that U1 and U2 are disjoint. Right? Now, consider the preimages of these sets. So consider the preimages f inverse U1 and f inverse of U2. Right? Now, f inverse of U1 is open because f is continuous. And f inverse of U2 is also open by continuity. Now, the next claim that I will make, and I'll have to erase this, is that f inverse of U1, so I'll write it here actually, f inverse of U1 and f inverse of U2 are disjoint. And it's very easy to see. We can just consider this diagram. So here's R, 0, and we have the R2 here, we had P2 here, and P here. So this is U1, and this is U2. This is the preimage. And this is the preimage of U2. And they have to be disjoint because if we were to suppose, by contradiction, that they were not disjoint, then everything in the intersection has to go both into U1 and into U2, which obviously contradicts f being a function. So they're disjoint. Now, one last thing is that obviously P belongs to the f inverse of U1, right? because 0 is contained in U1. And P2 belongs to F inverse of U2 because R2 is contained in U2. So what we've done is we created open neighborhoods around P and an open neighborhood around P2 that are disjoint, which means, and since P and P2 are arbitrary, this proves that X is a Hausdorff space. So the next result or property about Hausdorff spaces that I want to prove is that if X is a Hausdorff space, then every singleton set is closed. So let's prove this. Let P be arbitrary. And we want to show that this is closed. Or equivalently, that X excluding P is open. So how can we show this? So by definition of Hausdorff, there exist open neighborhoods U1 of P. Oh, well, let me first state that consider an arbitrary let's call it P2 and X, excluding P. By the Hausdorff property, there exist open neighborhoods U1 of P and U2 of P2, such that U1 and U2 are disjoint. Now what I want to notice is that U2 belongs to X excluding P, because U2 is disjoint from U1 and P is contained in U1. Now, the other thing that I want to note is that for every X belonging to X excluding P, there exists a UX, which is open, an open neighborhood, such that X belongs to UX, which can obviously be done because of the way that we construct this. So we have P, right here we have X, we just go through every single point in X, and we separate the two by disjoint open neighborhoods, and that's how we create UX, which means that the union of UX is an open cover of X excluding P. But since every one of UX, of these UX, is a subset, or I should say, subset. So here I should have written subset of X excluding P. We can state that the union of these is equal to X excluding P. Now, it's open, which means that X excluding P is open, from which it follows that that the singleton set P is closed, right? And since P is arbitrary, this works in general for every singleton set. And there's an easy corollary that follows from this, and it states that every finite set in a subset of Hausdorff space is closed, which is obvious from this because every finite set is a union of point sets and they're all closed, so every finite set is also closed. So the next important property about Hausdorff spaces is this really important result about sequences. And it states that if a sequence xi, obviously in a Hausdorff space, converges to a limit, then the limit is unique. So let's prove this. So we suppose by way of contradiction, that there exist two limits let's call them L and M. Now, the cases with more than two limits have to obviously contain the case of two limits. So if we exclude the case of two limits, we exclude the cases of more than two limits, right? Now, by the property, so first of all, actually, I want to discuss what's the definition of convergence in a topological space in general. And the definition is as follows. So for every open neighborhood, so a sequence xi converges to a limit L, or let's use N, if for every open neighborhood U of N, there exists an N0 such that N being greater than N0 implies that, that Xn belongs to U. Now what this means is that a sequence converges to a limit N if no matter how big or how small I pick the neighborhood around N, there will be an N0 that eventually all Xn with index bigger than N0 will be in that open neighborhood. So in other words, the sequence converges to N in that neighborhood. And we can use this definition to prove this. And the first thing that we do is by the definition of the Hausdorff property, there exist open neighborhoods let's call them U, L, and UN, such that, and L is contained in this one and M is contained in this one, such that they're disjoint. Okay? By definition of convergence, there exists an NL such that N being greater than NL implies that Xn belongs to UL. And the same for M. Okay. Now, consider the maximum of these two numbers. Now, for N greater than the max, Xn belongs to UL and Xn belongs to UM. Because we pick the bigger one of the two, it'll hold obviously for, we pick the bigger one of the two, it'll obviously hold for the smaller one. Now, UL and UM are disjoint, which is a contradiction. Which means that there is a unique limit. QED. Alright, so the next property, and the final one that I'll discuss today, of Hausdorff spaces is this important result about limit points. And it states that if a subset A of X has a limit point P, then and X being a Hausdorff space, then every open neighborhood of P contains infinitely many points of A. Now the first thing is the definition of a limit point. So P is called a limit point. If every open neighborhood of P contains at least one point of A. So a limit point is a point where every neighborhood contains at least one point of A, and we want to show that in a Hausdorff space every neighborhood contains infinitely many points of A. So let's prove this. Fix an arbitrary neighborhood U of P. By definition of a limit point. And by the way, this point has to be distinct from P, obviously. So by definition, there exists a distinct, so a point, so let me call it an R, or let's call it X in A, such that and X is distinct from P, such that X is contained in A and X is contained in U. Now, by Hausdorff, there exist open neighborhoods. Let's call them UX and UP, such that, and X is contained in UX and P is contained in UP, such that UX and UP are disjoint. Now, consider, so let me make more space actually. So consider UP intersect with U. Now, this set is obviously a subset of U. This set is open, and U is open, which means this set is open, right? Which means, and one last thing to mention is that X does not belong to UP intersect with U, because X belongs to UX and is disjoint with this set. So by definition of a limit point, there exists a Y in A, Y distinct from P, such that Y is in A and Y, such that Y is in UP intersect with U. And this is a new point in A that is contained in U, right? Because it's contained here and it's contained in U, which means Y is distinct from P and it's distinct from X, right? So by picking an arbitrary open neighborhood, we considered by the definition of a limit point, a point in A distinct from P that is in this neighborhood. by Hausdorff, we consider the two disjoint open neighborhoods around these 2 points, and we consider the intersection of that with a bigger one, and which is contained in there. And then we use this to generate another point in A that is contained in U. And we can keep going as long as we want, which shows that U contains infinitely many points of A. Since U is arbitrary, this works for every open neighborhood around P. So every open neighborhood of P contains infinitely many points of A, which completes the proof. So every open neighborhood around a limited point P contains infinitely many points of A. So that's it for today. I hope you enjoyed this video, and thanks for watching.